for homogeneous. Then we had this method where we found out v, if we have vx function, and when we multiply with the y1 which is given to us in reduction of order, then we can get another member of a fundamental set. Basically here we are using product rule, quotient rule, and we get a Wronskian term on the top. We also know the form of a Wronskian from the slides this, so as a result we find v through this expression, and then we have y2. Okay, so here are a couple of examples we did last time. Let me scroll to non-homogeneous system. So we discussed method of undetermined coefficient last time. Now for variation of parameter. Variation of parameter is also a method through which we can solve non-homogeneous differential equation. We can compute particular solution of non-homogeneous differential equation. Once we have particular solution, we will add it to the general solution of homogeneous to get the general solution of non-homogeneous problem. Okay, so if these y1 and y2 are member of a fundamental set, then we are looking for a particular solution, and we will make use of the members of a fundamental set to find that. Now y1 and y2 will be satisfying associated homogeneous problem. So you place the y1 and y2 here, and then with the function u and v. The reason we are placing ux and vx functions depending on u and v, because we want this particular solution not to be just come out to be a solution of homogeneous problem. Because if it doesn't depend on, if it's like a constant times y1 plus constant times y2, it is just a homogeneous, it's just a solution of homogeneous problem, right? But we want a particular solution of this non-homogeneous problem. So we insert of functions depending on this x, and then if we plug this entire expression back into non-homogeneous problem, and by further calculations solve for ux and vx, ux turns out to be integral of negative y2 fx over Wronskian. So this is a formula how you will find ux. You will be first finding fundamental set, and then fx is the right hand side, and then you have a Wronskian. Same way you find vx. Now this method will work if differential equation is of non-constant coefficient, if your right hand side is of any form. It doesn't have to be sine only or cosine only or exponential times sine, exponential times cosine. So this is kind of like will work every time. But the only problem here is sometimes this integration becomes very hard, or sometimes it is like impossible to even integrate. So you might have to sometimes leave the answer within an integral form. Whereas if the function fx on the right hand side is nice form, then you might use undetermined coefficient and get the solution explicitly and not get stuck with this integration here. So both the method have their pluses and minuses. But method of undetermined coefficient you can only use if your coefficients are constant of derivatives terms and the right hand side is nice. Okay, so this is how you get a particular solution. You don't add a constant after this integration, because if you add a constant, you are basically not just giving a particular solution, you are giving the full general solution of a non-homogeneous problem. Because you can see once you add a constant and if you multiply by y1, you are adding that general solution of homogeneous problem. So particular solution will not involve any constants. Okay, so this is method of, this is variation of parameters. Very straightforward method. Only sometimes this integration might be difficult to compute. Okay, so now tan x, this problem you cannot solve using method of undetermined coefficient, because right hand side is not in the form of exponential time sign, polynomial time sign, or those kind of forms which we discussed. So the only method available is variation of parameter. So I'll go very quickly on the steps. First homogeneous problem we will solve, and these slides are already posted on Blackboard, so you can have this work with you. Okay, they are already there. This is homogeneous problem. Lambda is plus minus I, the roots of this characteristic polynomial. Now, so what is fundamental set then? E to the power real part, which is 0, so will be just 1, and cosine times b is 1, so it's cosine x and sine x. So cosine x and sine x will form the fundamental set. So you can, the moment you pick your y1 and y2, fix it. Don't then further in the calculation change that this is my y1 and this is y2, because order matters. Like you have to keep, because you know in Wronskian order matter. If you change the order, Wronskian will have a negative sign. So fix y1 say as this, y2 as this, and then keep carrying that same y1, y2 throughout every calculation. Okay, find the Wronskian of them. Once you have a Wronskian, place a Wronskian here, y2, y1, and f is your right hand side, which is tan x in this case. F is tan x. So when you put all these things together, fx is tan x, then y1 I chose here to be cosine x, right? And y2 I chose to be sine x. So I will place my y1 here as per the formula minus y2, which is negative sine x, and then fx is tan, which I wrote it down as sine over cosine, and Wronskian is basically 1 of cosine x and sine x, so it's just 1. The next term, y2 is sine x, y1 is cosine x, and then you have function fx is tan x and divided by Wronskian, which is 1. So as you can see, here you have sine square x over cosine x, and here you will have sine over cosine, and cosine gets cancelled, just sine. So this is the expression eventually you get. Now you just have to integrate. This is easy to integrate. Now how will you integrate this expression? Yes, you sub, you can do. So which function you will? You can make use of cosine is used, because then sine times dx with negative will go to the du, but then there's one sine term left, which you have to again replace by square root of that if you want to, and then you again in the realm of now handling those two expressions. So you can do that way. Other way is, this is basically tan and secant, right? So you have a direct, so what I try to do in this is I just took sine square as 1 minus cosine square first. So we get this expression. Then you get secant and cosine x integral. Now you just have to, cosine x integral you know already. You just have to handle the integral of secant. And integral of secant, you know, from even from your table, or so you see, right, 1 over cosine is secant, and cosine square over cosine x is cosine x. So that's why you have a cosine x term here and secant x term here, and this one just comes along with it. An integration of secant, you have ln of secant plus tan, and this term here integral will give you sine term, and this term will get cancelled of this above term. So you end up in this particular solution. Okay, so integral of secant is ln of secant plus tan x. So I just place that.
And no constant.
Yeah, particular solution, right? So no constants. Particular solution will not involve any constant, but yes, once I place this particular solution, Once I add this particular solution with the general solution homogeneous problem, then we have full solution. Okay, so now we will add it to the general solution of homogeneous problem, and that's the general solution of non-homogeneous problem. So this is a strategy you will take in variation of parameter. Very straightforward method. Okay, so in method of undetermined coefficient, it's sure if the form is nice, you definitely end up getting a solution explicitly, and you don't have to do any integration in that method. But you have to choose the guess very, very carefully so that it avoids all that extra calculation if it doesn't work. Okay, so there is one more problem, cosecant. Well, you can see once you do this problem, you will end up in this answer if you try to do it by yourself later on, and use the same steps, y1, y2, formula of ux, vx, and put everything together, and you will get this. Okay, so now let me move to vibrating mechanical system. We have already covered all this. Okay, so I think I should start with this. Did I add my vibrating mechanical system slides in the okay, analyzing force acting on an object. So in the figure below, there is no figure right now here. Let me draw it quickly. So you have a spring attached to a mass here, and the length of, and let me put it through the center of gravity of it, so maybe from here to here, the length of this we will call as a natural length is L. Okay, so this figure is giving us natural length. Now making, like, maybe it might not seem, but this I am kept in the same height. So from here, then we release this mass and it gets stretched because of the spring constant and the force mg acting downwards. So now your new length, which was till here, is capital L till here, but from here onwards there is an increment in it which is little l, the extension. I'll call this diagram mass and equilibrium position. No external force is being applied to this system yet. And spring has stretched length L, little l. Okay, so now the third diagram, in which I will be applying external force to this mass, and it will be further stretching, getting stretched, will move down. It's might not look the same mass, but it's the same mass. M is not changing at all. And now at this time, if we consider this level, then it is, this height is L plus capital L plus small l, and from here to here the extension is little y, and this is due to the external force. Okay, So C, mass distance y below equilibrium position, and now spring has been stretched. Total length, his final length is capital L plus y, little l plus y. Okay, so this is the length. Maybe not write it down like this, just leave it. Okay, so you know the final length. Now we have to analyze this whole phenomena, and we have to set up a differential equation associated to it. So we have to balance all the forces. Okay, so what are the type of forces we have here? Let me name them as F1 is first force. Which one you will take as a first force here? Force due to gravity. Very good. So it's mass times gravity. Okay. Acceleration due to gravity. Okay. So now this is force, and then you have another force F2. Which one is it? Right. I mean, mass times acceleration we have already taken care of here. So which one is another force? Velocity? No. The one which is coming through. You are balancing the force. Spring. Right. Spring is making a force. Spring constant is also creating a force, right? So what's the name of that is restoring force. So restoring force, you have a restoring force here, and this I will denote as F2, and this will be equals to what?
Spring constant times the or little L.
What would be the sign of that?
What it might go if mg is positive, then we're calling that negative.
In that same direction it would be negative. But so in equilibrium state, mg will be balancing kl in this state B. So k is nothing but mg over L. So k is a spring constant here, and which law tells us that these forces balance each other? Okay, you think then another force F2, which I am writing down here is in the third diagram, is k times y plus L. The elongation through L and y will be causing another force in the backward direction. This is minus ky minus kl, and k being a spring constant, you have this. Okay, is there any other force?
Well, there's still mg, but since it's not an equilibrium.
Yeah, I already took an mg here. So is there any other force? Now I'm just collecting the forces. Any other force? I mean, this cannot happen without
Another force.
external force. So here F4, which is Ft, let me write it down, is external force, by which you are pulling this mass downwards, and it causes displacement y. Any other force? Because I named it as F4, so I skipped one force in between. So what's my F3 then?
This is from the perspective of the mass, right? If you're drawing a force diagram, you're talking about from the mass.
Yeah, so we are trying to see if this kind of situation physically is happening. So string causes mg is there, then we further stretch it, then again due to that stretch backwards, external force by which we are stretching, and what else? It won't be in vacuum, right? This whole thing is not in a vacuum. So there are forces from air resistance forces. Yeah? Air resistance. Okay. So resisting forces. And we will call them as minus c dy over dt, and this came in an idealistic kind of situation. Most of a textbook always takes in this scenario resisting forces to be negative c times rate of change of this y. Okay, with absolute sign it would be just nothing but dy over dt. C is called as damping factor. The C is computed through other experimental data, and the unit of C is kept consistent with such a manner that eventually the C times this results in the force units. Now I would not go into how they really compute the C, but that is what your resisting force is. Okay, we are assuming C to be positive. That is the reason we placed a negative sign here, because it will cause decay in a motion. Okay, so these are all the forces. Let's balance all of them. So net force on this system will be, whole system, the total force is F1 plus F2 plus F3 plus F4. Now this net force is equals to what? So right, I mean this, I am writing all the forces. mg, F2 is minus ky minus kl, F3 is minus c dy over dt, and F4 is F4. Now what is this total equals to? So we are now applying Newton's law of motion to balance these forces. So what does it say? It says that mass times acceleration is equals to total force. Okay, so which law of Newton's is it? From Newton's second law of motion. Because the third law is just saying every action has equal and opposite reaction. First one is saying that without a force nothing moves. Once we apply, objects start moving. And the second one is which helps in balancing the total force. So I will put here m, and what is acceleration? Acceleration is gravity we have already considered, g. But acceleration of this mass, when we have external force applied and it got pushed down, right? So now it has its own way of movement apart from the equilibrium. Equilibrium, it's staying like that. And then we pushed it a little bit downwards. Then it starts moving up and down, up and down. So now this up and down motion, there is a displacement which it caused. So how will you find the acceleration? How is it related to displacement? Velocity. d by dt is velocity. Then acceleration is second derivative of that, right? So d2y over dt squared. So mass times acceleration is this whole thing. So okay, fine. So let's now, this is the equation we end up into, let's divide this throughout by can I do this? Can I divide it throughout by m? Why? Because mass is not 0. If mass is 0, nothing is happening here. Mass is non-zero, so we can divide it. You have to be careful whenever we are dividing. We should not try to divide something by 0. Okay, so that means d2y over dt square is nothing but your mg here. So g minus k over my minus k over ml minus c over m dy over dt plus f4 over m. Okay. So now we will rename these constant, but as right now itself you can see, is there any term which is getting cancelled? What is G? What is mg and relationship between mg and kl? They are equal, right? mg is equals to kl. So that means these two forces cancel each other. So here we can get rid of this term with this term, and we are left with d2y over dt square is equals to negative k over m y minus, and let me push these terms y and dy over dt on the left hand side. So that will give us plus k over m y plus c over m dy over dt is equals to f4 over m. So can you see that we end up getting here, differential equation. So that's exactly what vibrating mechanical system is all about. So we will be solving second order non-homogeneous differential equation. So the solution of this is what? What is the solution of this? Like, I mean, I don't want explicit solution, but physically, what is the solution giving us? Y. What is Y? Y is displacement, which happened when I applied external force. So we want to see when this mass, I stretch it down with certain force and I release it, it will go up, down, and with damping factor, its amplitude will decrease, right? So we want to see at particular time t, how much is that stretch, y. So when I had y stretch and then I released it. Now it may not go more than y, and then further less than y, then something. So y kept changing with time. So this function yt, which we will solve for, is telling us how displacement of this mass will change with time t. Once we will solve this. So at particular time t, it will give us exactly from equilibrium what is the displacement of this mass. Okay, so this is what differential equation we set up and the solution significance in this physical situation. Okay, so you have seen now, given a situation, you balance the force, you apply Newton's law, and then you try to extract a differential equation. Now depending on how many forces are there, if now this is hanging, maybe in an exam I can ask you something, it's not hanging but it's placed on a table and it's hooked from a wall and there's a spring and a mass, and somebody pulls it towards them, and that mass moves on the table. Now mg is not balancing that motion. It's a force of friction which is on the table. But if I say there is no force of friction, then you have to balance all the forces and you have to set up a differential equation. Okay, so it would be good exercise that I have explained the whole problem with hanging. Try it on some surface, this mass moving with y displacement. Okay, now there is interesting, so as you have noticed, this is a second order differential equation. So we obtained second order non-homogeneous. What is C, by the way? What is C doing here? This C. C is causing damping. And it's true that whenever you are seeing the second order non-homogeneous differential equation, every time the y prime term will cause damping. Now if there is no y prime term in this example which is given to you, say they give you a differential equation which doesn't have a y prime term at all, that means that motion will not be affected by air resistance. There is no damping there. And that you can now understand through this derivation completely, that there would not be any damping in that system. So amplitude will not be like, so you would see in the examples, you would not have a, as time approaches to infinity, it won't be going towards zero because of not having a damping factor. Okay, it keep oscillating. It's not having an idealistic situation, keep oscillating, say in vacuum, but in air it will be decaying eventually. Okay, when acceleration is constant multiple of constant negative multiple of displacement, object is said to be in, this is a very famous motion in physics, that when acceleration is constant negative multiple of displacement, which means I am avoiding this y prime term here because this is acceleration, and if I push this term on the right, this will be negative, k and m being positive, this will be negative constant multiple of displacement. We are, say, not taking external force. Then in that situation, object is said to be in simple harmonic motion, SHM. Simple harmonic motion. So now let's solve this differential equation, break it into all possible cases when external force is not there or external force is there but there is no decay and all those kind of things, and then solve this. And then once you have examples, you can apply each case into that scenario. Okay, so cases here. If C is 0, then motion is undamped. So if you see undamped terminology somewhere, then you definitely can assume C is 0. If Ft is 0, and Ft was my external force, I named it with F4, but F4 and Ft are same. If no external force, motion is called free motion. If Ft is 0 and C is 0, both of them are 0, then we will call, then basically this motion will be in SHM. It will be simple harmonic motion. Okay, so these are the cases. Now let's start solving them. So case 1. no external force, no air resistance. How will displacement change? Okay, so we have this differential equation, then y double prime of t plus k over m, right? This term was there. Y prime term will not be there, external force will not be there, it's just this. You all agree? It will be just this. So from here, I removed this term and the last term. So it's just this term and this term. Okay. So just for convenience sake, mass is always positive and spring constant we always take it as positive. So I will denote this whole fraction with a positive quantity, omega square. Okay, you will see this omega has a name slowly, but y at 0 initial displacement is y naught, y prime at 0 initial velocity is v naught. Here we are assuming c0, f0, k positive, m positive. Okay, sometimes I write capital M and sometimes I write small m. In this context they are same. Sometimes it just forget, but they all are same here. Okay, so how will you solve this differential equation then? So you have y double prime t plus omega square yt is equals to 0. So how will you solve this differential equation?
WT is just a constant.
W is just a constant. And is it homogeneous? Constant coefficient, homogeneous. So which method we can apply? No, characteristic polynomial approach, right? Okay, so let's write down the characteristic equation. Lambda square plus omega square is 0. That will imply lambda is plus minus omega I. So our homogeneous, or the general solution in this case, will be what? Can you tell me the first term? Cosine what? Cosine omega and then t omega t. Okay. Now this expression is not what you really encounter in any physics textbook which you open is describing your simple harmonic motion. What you see in every textbook is when they say something is simple harmonic motion, they have displacement either in cosine or in sine. But they don't have cosine and sine term both coming in the expression. So now our goal is to get that nice expression which you always find in every single textbook for simple harmonic motion. So how can I merge both these terms into a single term? This is the main trick of vibrating mechanical system overall. Main trick, but it's always like, I don't know, you have seen it in high school, but we did. This is like this trick is being taught in high school trigonometry. Or maybe I can go a little bit upper level of, after high school you have a secondary, that phase of 2 years. You have addition of two terms, and meanwhile, since as you are thinking, I will find this C1, C2 and place them here as well. And you think how you can merge these two terms in a single cosine term or a single sine term. And I'm computing my C1, C2 during. In meanwhile, okay, so y0 is C1, y prime 0 will be, you have here y prime t. Okay, now constants are not there. We have specific like initial displacement and initial velocity, and we still have to merge these two terms. Okay, any suggestions? Any suggestions how we will proceed? You have done those things like cosine C plus cosine D, or cosine C plus sine D. Those formulas, sum, difference, product of cosines and sine. Those are helpful here. Not really. I will multiply by an A and I will divide by A. There is a reason why I am doing that. And this is a trick here. Then, once I do this, I have tried to make the coefficient common outside of both the terms, but meanwhile I will assume, if I want eventually a cosine out of this yt, what should I assume this y naught over a to be? No, this cannot be 0 because initial displacement is there. So we have to so you have to sum difference formula. What is cosine a plus b? Cosine a plus b inside bracket. Come on, cosine a plus b. Right, tell me the formula in terms of a and b, cosine a and cosine b. So cosine a plus b is equals to what? Cosine of sum of two angles will involve cosine of each angle minus the sine of each angle, right? And sine of sum of two angle is sine of first angle cosine of another angle plus cosine of that first angle and sine of another angle. So like this you have sine and cosine sum of angles. So in this, if I want eventual expression in sine, then I will be assuming this to be sine of something and this to be cosine of something. But if I want final expression in cosine, then I will assume this cosine of something, some angle, I don't know which one, and this one as sine of that angle. Now if I make this assumption, then cosine of phi cosine of omega t plus sine of phi sine of omega t will be nothing but cosine of phi minus omega t, right? So here you have formula cosine of, this you should know, cosine of a plus b but if you have sine of a plus b, then you have So if you want a final expression in cosine, you will assume this to be cosine cosine, because cosine cosine and sine sine can give you cosine. If I place a negative sign here, it will be a plus sign here. So if I want total expression in sine, then I should assume this to be sine, because sine cosine cosine sine can give me sine. So if I want this addition to be sine, then I will be assuming other way around, this to be sine and this to be cosine. If I want this whole thing to be cosine finally, then I will assume this to be cosine, because cosine cosine together and sine sine together can only give me cosine. Right? Cosine cosine and sine sine together can give me cosine. Sine cosine together can give me sine. So here I am making cosine cosine together because I want eventually in cosine. And if you want eventually in sine, you take sine cosine cosine sine. Is it making sense? So the reason of choice here is, okay, now let's move on, then we will see. So yt turns out to be then a cosine phi cosine omega t plus a sine phi sine omega t, and that will give me a cosine of, by this formula, phi minus omega t. So I converted the sum of cosine and sine into just cosine, and to do that we have to divide, because the reason I cannot do it right here, I don't have a coefficients which can give me just this to be as full as cosine thing. Not so that's the reason. Okay, so how we will compute this a and this phi, because these are not known to us yet. So cosine, so we have two equations here. Cosine of phi is y naught over a, and sine of phi is v naught over omega a. So that means if I want to simplify this, solve these two equations for a, what will I do? Both are unknown here, phi and a both are unknown. I have two equations, two unknown. How will I get rid of phi to get a, or get rid of a to get phi? To be honest with you, when you will be solving examples, you might see now this is theoretical stuff going on, but when you will be doing example, this trick and this thing is what you have to do again and again. So you will find that time that this is very important. So how will I get rid of phi from these two equations? Another important trick.
Get rid of it, or
Yeah.
get it outside of cosine?
Get rid of it, because it cannot go outside of cosine. It's an angle. Cosine of this angle is this.
That's why I was asking, because you could say arc cosine, right? Or
Um,
equal to phi. That's why I was asking.
But then the problem comes, if phi is arc cosine of this and phi arc sine of this, what exactly is phi? So somehow you have to take account of both the equation. You cannot get a value just from one equation. And if you try to, you would get a wrong sign in terms of phase. Because this is kind of like a lag and this is a phase in physics. And this A will be amplitude of this Y. So that's the reason I place these A and like this. Well, any other way, any trig identity you know, which can get rid of this phi completely completely. We don't have any phi. Trig identity. Trig identity. It's much easier. Trig identity, by which you can get rid of cosine phi, sine phi completely.
Square and then add together.
There you go. That's exactly what I mean. So cosine square plus sine square is 1. Okay. So cosine square phi plus sine square phi being 1, we get rid of this phi completely. Easy, right? We don't have phi now. So we can solve for a. So a square, make a common denominator here. So let's not skip steps. So 1 is equals to omega square y square, just making a common denominator, and then omega square a square is omega square y naught square plus v naught square. So a square is y naught square. This is amplitude of this oscillation, v naught square over omega square, and a is amplitude. We will be considering positive because that's just a distance, and it would be positive square root of this. Now how will I get rid of a and get my phi? Now this is good. This is very good. We got an amplitude now of the oscillation. I will place this expression up here, so it's not like something which you don't know. And you have a cosine of omega t, you know, minus phi. So now only thing which you want to know is phi. So how will you find phi? So yeah, these equations are here. Two equations. Very good. Very good. That way we can incorporate both the equations and we are not just making use of one. So divide them. So cosine sine phi divided by cosine phi is nothing but, what is sine phi? V naught over omega a, and then this whole thing gets divided by y naught over a. So you will end up in v naught over omega a times y naught times a gets cancelled. So v naught over y naught omega, and that's your tan phi. So phi is arctan of, and as you can see now, what is v naught over omega? Your C2 constant which you computed. Y naught was your C1 constant which you computed in homogeneous problem. So this is basically initial velocity over omega times y naught. That will give you the angle, the phase by which with time this graph of cosine will shift, will change. Okay. So now a couple of terminologies here related to physical significance. Omega here is square root of k over m. Yt here, the solution of this is a cosine square root of k over m t plus phi. Did we had plus or we had minus? Let me go back and check. We had minus, so if we had minus, so right, let's stick to the minus. And then we have here minus as well, but you can even get it into a plus. So right, and then your period is 2 pi over omega, and by period we mean time taken by one oscillation. Time taken by one oscillation. Frequency, number of oscillation per second. And in this situation, when you have simple harmonic motion, it will be omega over 2 pi, because frequency times period is 1. And here by period I mean here capital D. So these are some physical terms which you would be using in examples when you are doing simple harmonic motion. Okay, so now let's move on to what are the possibilities when, say, we have a damping factor. So this is undamped, there is no damping here, but let's introduce damping but remove external force. Okay, so this is exactly the law I stated before, and undamped means there is no reduction in amplitude. Now this graph here shows us the y-axis is displacement, x-axis is time, how the displacement changes with the time, and this from here to here it's one cycle. So, and the length, which is from this peak, the maximum height here, is nothing but your amplitude. So if you have, say, I mean, most of you have seen this in physics when you are doing simple pendulum, that once you have a bob up here in the equilibrium position, and due to external force it goes up here and then it comes to here, so this is half cycle here, but if it goes here till here and then come back, that's a one full complete cycle here. So amplitude is the distance from here to here. Okay, so that's an amplitude. Okay, this is undamped, no friction, no air resistance. Unforced, undamped, we already solved this one. Now damped vibration. Now there is a air resistance or a friction if it's on the table, friction. If it's in the air resistance forces. So oscillation will die out. Eventually it will stop. Mass cannot keep fluctuating up and down, it will stop at one point of time. So there is a lot of ways this mass can stop. Say the displacement keep little increasing and then further dies out completely. It keeps oscillating and then dies out, and there is no oscillation up here, and it ran up very, very fast, it decreases and then try to little bit increase. So these are the three situations of damping, and they will be depending on the damping constant C, which type of medium we are. So what causes damping? This factor C causes damping. The Y prime term coefficient causes damping. Okay, So let's see which case will give us so when we have damping thing, we have this term. So let's write down what is the solution of this problem, and then we will see, we will classify each form of a solution into the situation we are in the above graph. Okay, so let's write down this is again a second order homogeneous problem. No external force here, but resistance is there. You might say, well, if external force is not there, why even the object is shaking, right? Because you're not pulling. Well, air resistance is there, so it causes it to move up and down. Okay, so constant coefficient, second order differential equation, how will you solve? Characteristic polynomial. So Cp for this is lambda square plus C over m lambda, very good, plus k over m equals to 0. What are the roots? Lambda is, let's apply the quadratic formula here, minus b plus minus b square minus 4ac over 2a, and a is 1 here. So this is there, so let's simplify this little bit, minus c plus minus, if I multiply m in this, I will multiply m in the bottom, so I can pull this m out. So c square minus 4km divided by 2m. Now the behavior depends on how this c is related to this km, because if c square is equals to 4km, then you don't have any square root, right, here. So if c square is equals to 4km, you have repeated roots, and the solution will be e to the power this times t plus t times e to the power this. So there is exponentially decay, because c is positive and 2m is positive, right? This coefficient is positive, but here it has a negative sign, so there's a decay, and it doesn't have cosine and sine then at all, so there is no fluctuations and dying out. So this sad situation will either be representing this graph or that graph if c square is equals to 4km, right? And then we will consider c square bigger than 4km, distinct roots, and c square less than 4km. These are the only possibilities. 3 possibilities. Roots can be distinct and real, roots can be complex, then we are in this situation, and roots can be repeated for a second degree polynomial, right? Okay, so let's see, when is it underdamped? Well, underdamped is, we call it as underdamped when we have this kind of situation, and as you can see here, lambda is minus c plus minus square root of c square minus 4km divided by 2m. So right, so then in that case, when c square minus 4km is less than 0, because then only we can get complex roots, right? So if this is less than 0, this will have this phenomena, and yt will be nothing but c1 e to the power minus c over 2m times t cosine this part, square root of c square minus 4km divided by 2m, this is angle, plus c2 e to the power minus c over 2mt, the coefficient, real part of the root, and then the imaginary part of a root. This is inside, this whole is an angle of sine. So because of this being positive, this term is positive, and as time approaches to infinity, what will happen to the solution? This will go to 0, because cosine and sine values lie between -1 and 1. So this is a bounded function between -1 and 1, and this goes to 0 very fast, and it will stay finite, so eventually this will go to 0. So it will die out eventually, but keep oscillating because of cosine and sine terms appearing. Okay. Well, if I want to keep a positivity of this, because this I am assuming to be negative, I can reverse the sign here, which will be helpful, because then in that case it will be positive, 4km minus c square, because angle we don't want to be negative. Okay, so here frequency of this is different. Frequency of SHM you have already seen was omega over 2 pi, but frequency of this will be square root of 4km minus c square divided by 2m times 2 pi. Okay. Now we are in the case when it will try to take a little jump, try to little increase, and then decrease very rapidly. This is over. Over case comes when you have discriminant to be positive. So your solution in that case, if it is positive, you have real and distinct roots. Real distinct roots will give you c1 e to the power minus c plus square root of c square minus 4km over 2m times t plus c2 e to the power minus c minus square root of c square minus 4km over 2m times t. Now this is negative, this is causing decay in the solution. This is causing decay till this term doesn't take over to the c. When c is larger than this, and which happens when it is very in short period of time, very short period of time, it will try to increase, but then because of this negative sign and t gets large, this negative sign pulls it down completely. Okay, so it eventually decreases, but now because of this exponential behavior, it will not show you oscillation here. Displacement will not become positive, negative randomly. Displacement remains positive because of exponential term is always positive. Exponential function is always positive. So y remain positive here, and as time approaches to infinity, it definitely dies out. It goes to 0. Okay. When discriminant is 0, this is the last case, and then we will be done. Just this one. C square minus 4km is 0. Critically damped situation. In this situation, your roots will look like minus c plus minus, and this is gone, over 2m. So your solution will look like c1 e to the power minus c over 2m times t plus c2 t e to the power minus c over 2m times t. So you can see this is both is negative, right? So that's the reason it will decrease. But when time is positive, right, depending on the choice of the C1, C2 is nothing but every time you will get these C1, C2 depending on your initial velocity and initial displacement. So this is going towards, this is decreasing very fast when time is small. The reason is both these terms are causing a decay here. then as time increases and positive, this might try to increase, but eventually growth of exponential is faster than the linear growth of a function t. So this will overpower the linear growth of time. So decay process of exponential will be faster as time, even though time increases. So therefore this will again goes to 0. So these are the only three phenomena of damping which can happen when you have no external force and a resistance. Now you can use these examples to work out your problems. We will see forced vibrating mechanical system in next class.